Picture this. You're walking through the French countryside in the year 1150, and you hear something that doesn't quite fit. It's not the usual sounds of medieval life. No clanging of blacksmith hammers from individual workshops. No grinding of grain by hand. No rhythmic beating of cloth with wooden paddles. Instead, you hear a symphony of mechanical precision. Water rushing through channels, wooden gears clicking in perfect rhythm, hammers pounding with relentless consistency. You've stumbled upon something that would make modern factory managers weep with envy. A Cistercian monastery that's basically running a medieval industrial complex powered by nothing but flowing water. Most people think the Industrial Revolution started in the 1700s with coal and steam. Wrong. The real pioneers were a bunch of monks in white robes who figured out how to harness rivers like they were taming wild horses. These weren't just religious communities sitting around copying manuscripts all day. They were engineering masterminds who turned trickling streams into roaring production lines that could outwork entire villages. We're talking about water-powered factories that operated 24 hours a day, producing everything from flour to finished cloth to iron tools, all while the rest of Europe was still doing things the hard way. The Cistercians didn't just build a few water wheels and call it a day. They created integrated manufacturing systems that would make Amazon's logistics team jealous. One stream could power a dozen different operations in sequence, each wheel perfectly positioned to maximize the water's energy before passing it along to the next station. It was like a medieval assembly line, except instead of conveyor belts, they used carefully engineered waterways that flowed with mathematical precision. Here's what blows my mind about these monastic engineers. They figured out how to convert the random chaos of a flowing river into the organized power of a factory floor. They understood concepts that wouldn't be formally written down by scientists for another 500 years. Hydraulic engineering, gear ratios, power transmission, workflow optimization. All of this was happening in monasteries, while kings were still fighting with swords, and most people thought the earth was flat. But this wasn't some accident of medieval ingenuity. The Cistercians had a secret weapon that most people overlook. They were obsessed with efficiency in a way that bordered on the fanatical. Their religious rule demanded that everything be done with maximum productivity and minimum waste. Idle time was basically a sin. So when they looked at a bubbling stream, they didn't see a pretty water feature. They saw untapped horsepower, just waiting to be harnessed. Let's follow one of these streams from its source to see exactly how they pulled off this medieval miracle. Picture a mountain brook, maybe 30 miles from a Cistercian abbey, tumbling down rocky slopes, with enough energy to power half a village if someone just knew how to catch it. The monks didn't just throw a wheel in the water and hope for the best. They spent years studying that stream, measuring its flow during different seasons, calculating exactly where to place their first intervention. The magic started with something called a diversion weir, basically a small dam that didn't stop the water completely, but convinced it to change direction. Think of it as politely asking the river to take a slight detour through your factory, instead of just flowing straight to the sea. But here's where the Cistercians showed their genius. They didn't just divert some water, they controlled exactly how much water went where, using a system of channels and gates that could be adjusted based on whether they needed maximum power for the grain mill or steady flow for the textile operations. The engineering behind these diversions was surprisingly sophisticated. The weir itself was built from carefully fitted stones, angled just right to create the perfect amount of turbulence. Too steep, and the water would rush past without being captured. Too shallow, and there wouldn't be enough pressure to fill the channels properly. Medieval monks were basically fluid dynamics engineers who happened to pray 7 times a day. From the weir, the captured water flowed into what they called a leat, a man-made channel that was like a medieval superhighway for water. These channels were dug with slopes calculated to maintain perfect flow speed. Too fast, and the water would erode the banks and create flooding. Too slow, and it would lose the energy needed to power the wheels downstream. Some of these leats stretched for miles, winding through valleys and across hillsides with the precision of Roman aqueducts. But the real genius wasn't in capturing the water. It was in what came next. The leat led to a mill pond, which sounds simple, but was actually a masterpiece of hydraulic engineering. This wasn't just a pond. It was a carefully designed reservoir that served as both a battery and a regulator. During high water periods, the pond stored excess flow. During dry spells, it released stored water to keep the wheels turning. The size and shape of these ponds were calculated based on the seasonal flow patterns of the specific stream and the power requirements of all the machinery downstream. Standing at the edge of one of these mill ponds, you'd see something that looked almost modern in its precision. Sluice gates controlled exactly how much water flowed out and when. Stone channels directed the flow with mathematical accuracy. Water levels were marked and monitored as carefully as a modern power plant monitors its turbines. The monks had essentially created a hydraulic computer that automatically managed power distribution across their entire operation. The water leaving the mill pond entered what they called the head race, the final channel before the actual machinery. This was where the real magic happened. The head race was designed to deliver water to each wheel at exactly the right angle, speed, and volume. Different types of wheels needed different water conditions, and the Cistercians had figured out how to customize the delivery for each application. Here's where things get really impressive. Most medieval mills had one wheel doing one job. The Cistercians created sequences of wheels, each one positioned to catch the water after the previous wheel had used it. The first wheel might grind grain using the maximum water pressure. The slightly slower water would then hit a second wheel operating the fulling stocks for cloth production. The even gentler flow would power a third wheel running the bellows for the forge. Finally, the nearly spent water would turn one last wheel operating smaller tools before flowing back to the original stream. This cascade system meant they were squeezing every possible bit of energy out of each drop of water. It's like if you could use the same gallon of gasoline to power your car, then your lawnmower, then your leaf blower, and still have enough left over to run a small generator. The efficiency was absolutely staggering for the medieval period, or any period really. The water wheels themselves were marvels of wooden engineering. The Cistercians didn't just build basic paddle wheels like most mills. They created specialized wheels designed for specific tasks. Overshot wheels, where water hit the top of the wheel and gravity helped pull it around, were used when they needed maximum torque for heavy grinding. Breast-shot wheels, where water hit at about shoulder height, provided steady, consistent power, perfect for textile work. Undershot wheels, powered by fast-flowing water hitting the bottom paddles, were used for operations that needed high speed rather than heavy torque. But the real innovation wasn't in the wheels themselves. It was in what came after the wheels. The Cistercians had figured out how to transmit power throughout their workshops using an intricate system of gears that would make a clockmaker proud. Each water wheel connected to what they called a pit wheel, a large wooden gear with teeth carved from hardwood. Positioned horizontally just above a stone-lined pit, the pit wheel meshed with a vertical gear called a wallower, which transferred the horizontal rotation of the water wheel into vertical rotation that could be transmitted through the ceiling to upper floors or across the workshop to distant machines. From the wallower, power flowed to the great spur gear, a massive wooden wheel that served as the main distributor of mechanical energy throughout the facility. This gear system was like the electrical grid of the medieval world. Just as modern factories distribute electricity to different machines, the Cistercians distributed mechanical power through their wooden transmission system. Stone nuts, smaller gears made from the hardest available wood, connected individual machines to the main powertrain. The gear ratios were carefully calculated to provide exactly the right speed and torque for each specific task. The sophistication of these power transmission systems was genuinely remarkable. A single water wheel could power grinding stones on the ground floor, operate hammers in the basement forge, drive spinning wheels on the second floor, and run saws in the carpentry shop, all simultaneously. The monks had essentially created a mechanical internet, connecting every productive activity in their community to a single, renewable power source. What made all this even more impressive was the precision required to make it work. Every gear had to be perfectly aligned, every bearing properly lubricated, every drive shaft carefully balanced. One misaligned component could jam the entire system, shutting down multiple operations across the monastery. The monks developed maintenance routines that would put modern factory managers to shame, with detailed inspection schedules and preventive maintenance procedures that kept their medieval machinery running smoothly for centuries. The applications of this water power were limited only by medieval imagination and engineering skill. In the grain mill, massive grinding stones weighing several tons were turned by the precise application of water power, producing flour with a consistency that hand grinding could never achieve. The stones themselves were works of art, carved with channels and patterns that created the perfect grinding action, dressed and maintained with tools that were themselves powered by the same water system. Adjacent to the grain mill, you'd find the fulling stocks, massive wooden hammers that pounded freshly woven cloth in a rhythmic dance of water and wood. This process, which transformed loose woven fabric into the tight waterproof cloth that made medieval wool so valuable, required precise timing and consistent pressure. The water-powered hammers delivered hundreds of blows per minute with mechanical precision that human workers could never match. But perhaps the most impressive application was in the forge, where water power operated both the bellows that maintained the fire and the massive tilt hammers that shaped iron into tools and hardware. Watching a water-powered hammer strike red-hot iron was like witnessing the birth of the Industrial Revolution, centuries before anyone knew what that term meant. The rhythm of the tilt hammer was hypnotic, a mechanical heartbeat that echoed through stone walls and could be heard for miles. But what most people don't realize is that controlling this beast of a machine required the kind of precision that would make a Swiss watchmaker nervous. The cam system that operated these hammers was pure medieval genius. Water power turned a horizontal shaft fitted with wooden cams, basically wooden bumps positioned at exact intervals. As the shaft rotated, each cam would lift the massive hammerhead, then release it to fall with crushing force onto the anvil below. The timing had to be perfect. Too fast, and the hammer would bounce off the iron before it had time to shape properly. Too slow, and the metal would cool before the next blow. The monks figured out that a hammer weighing 200 pounds should strike roughly 100 times per minute for optimal iron working. They achieved this by calculating the exact size and spacing of the cams, the gear ratios needed to convert wheel speed to hammer speed, and the precise moment when each cam should release its load. But here's what really shows the sophistication of these operations. They weren't just powering one hammer. A single water wheel might operate 3 or 4 hammers simultaneously, each one timed to strike at different intervals. The result was a percussion symphony of iron shaping that could produce more finished metalwork in a day than a traditional blacksmith could manage in a week. One monastery's forge could turn out enough horseshoes to supply an entire cavalry unit, plus the nails, tools, and hardware needed by the surrounding community. The bellows system was equally impressive. Instead of having someone pump air manually, a job that would exhaust even the strongest worker, the water wheel operated massive leather bellows through a system of cranks and connecting rods. These weren't the small hand bellows you might see in a colonial museum. We're talking about bellows the size of small rooms, capable of maintaining forge temperatures that could melt bronze and keep iron white hot for hours at a time. The mechanical advantage was staggering. Where a traditional forge might struggle to maintain proper heat for more than a few minutes, these water-powered systems could keep fires roaring all day long. The consistent airflow meant more efficient burning, higher temperatures, and the ability to work larger pieces of metal than ever before. Some monasteries were producing iron goods that wouldn't look out of place in a modern blacksmith shop, except they were making them 800 years ago using nothing but water and wood. Moving from the forge to the tannery, the innovation continued. Bark mills powered by water wheels ground oak bark into the fine powder needed for leather tanning. This might sound simple, but anyone who's tried to grind tree bark by hand knows it's like trying to powder concrete with a mortar and pestle. The water-powered mills could process tons of bark in a single day, creating the consistent, fine powder that made medieval leather both durable and supple. The grinding mechanism itself was fascinating. Massive stone wheels, some weighing over a ton, rolled around a circular stone track, crushing bark between them with incredible pressure. The water wheel provided the steady, relentless power needed to keep these stone monsters moving in their endless circle. The ground bark was collected through carefully designed chutes and stored in covered bins that protected it from moisture, because wet tanning powder was about as useful as soggy gunpowder. What made this whole system even more remarkable was how the monks organized the workflow. This wasn't random machinery scattered around a courtyard. Every workshop was positioned along the water channel in a specific sequence that maximized efficiency and minimized waste. Raw materials flowed in one direction, finished products flowed out in another, and the water that powered everything followed its own precisely engineered path through the entire complex. The grain processing operation alone was like a medieval assembly line. Raw grain came in at the upper level, where it was cleaned and sorted using water-powered fans that blew away chaff and debris. The clean grain moved down to the grinding floor, where multiple sets of stones operated at different speeds for different types of flour. Coarse meal for animal feed was ground quickly with widely spaced stones. Fine flour for bread required slower grinding with precisely aligned stones that had been dressed, their surfaces carved with grooves, to create the perfect grinding action. But the real magic happened after grinding. The flour moved to the bolting room, where mechanical sieves powered by the same water system separated different grades of flour with precision that hand sifting could never achieve. These weren't simple screens. They were complex mechanical devices with multiple levels of increasingly fine mesh, each one vibrated by wooden cams that ensured consistent separation. The finest flour rose to the top, ready for the monastery's own bread making or for sale to wealthy customers who could afford premium products. Coarser grades were collected at different levels, each one destined for specific uses. Nothing was wasted. Even the coarsest meal found its way to the animal feed stores or the brewery, where it became part of the ale-making process. Speaking of brewing, the monasteries had turned even this ancient craft into a precision operation. Water-powered mills ground the barley and other grains to exact specifications. Mechanical stirring devices, operated by the same gear systems that powered everything else, maintained consistent mixing in the brewing vats. Temperature control systems used water flow to regulate fermentation temperatures with an accuracy that modern brewers would envy. The scale of these operations was genuinely industrial. A typical Cistercian monastery could produce enough ale to supply not just their own community of perhaps 200 monks and workers, but also the surrounding villages and travelling merchants. Their standardized production methods meant that ale from a Cistercian brewery in France would taste remarkably similar to ale from their sister monastery in England. Quality control centuries before anyone had invented the term. But perhaps the most impressive example of medieval automation was in textile production. The fulling stocks I mentioned earlier were just one part of an integrated cloth-making operation that would make modern textile manufacturers jealous. Water power operated every stage of the process, from cleaning raw wool to finishing the final fabric. The wool preparation area used water-powered washing machines, and yes, they actually had washing machines in the 1200s. Wooden paddles, operated by cams and cranks powered by water wheels, agitated wool in large wooden tubs filled with soapy water. The mechanical action was gentler and more consistent than hand washing, producing cleaner wool with less damage to the fibers. After washing, the wool moved to carding machines that combed the fibers into parallel alignment. These weren't the hand cards used by individual spinners. They were mechanical devices with hundreds of wire teeth that processed wool faster and more uniformly than human workers ever could. The carded wool was then ready for spinning, which was also mechanized using water-powered spinning wheels that could produce thread with consistent thickness and strength. The weaving came next, and while the actual looms were still operated by human weavers, water power was used to wind bobbins, prepare warps, and operate other preparatory machinery. The result was a production line that could turn raw fleece into finished cloth in a fraction of the time required by traditional methods. But the real innovation was in the finishing process. After weaving, the cloth went to the fulling stocks, where water-powered hammers pounded it in a bath of clay and water. This process, which transformed loose woven fabric into dense, waterproof cloth, was the secret behind medieval Europe's textile wealth. The mechanical fulling stocks could process cloth with a consistency and intensity that human workers could never match. The hammers themselves were marvels of engineering. Each one weighed several hundred pounds and was lifted by wooden cams, then released to fall with precisely controlled force. The rhythm was critical. Too fast, and the cloth would be damaged. Too slow, and the fulling process wouldn't work properly. The monks had figured out the exact timing needed for different types of cloth, from light woolens to heavy felts. After fulling, the cloth moved to water-powered stretching machines that pulled it to exact dimensions while it dried. These tensioning devices used a system of ropes, pulleys, and adjustable frames that could accommodate different fabric widths and maintain consistent tension throughout the drying process. The final result was cloth with uniform dimensions and properties, standardized products that commanded premium prices in medieval markets. The economic impact of all this mechanization was staggering. A single monastery could outproduce entire regions using traditional methods. They weren't just competing with local craftsmen. They were essentially operating in a different economic category altogether. Their water-powered factories could produce goods faster, cheaper, and often better than anything else available in medieval Europe. This industrial capacity translated into enormous wealth and influence. Cistercian monasteries became economic powerhouses that funded cathedrals, supported universities, and even influenced royal politics. Their success wasn't just spiritual. It was built on the rock-solid foundation of superior technology and more efficient production methods. But managing all this mechanical complexity required organizational skills that were just as impressive as the engineering. The monasteries developed detailed operational manuals, maintenance schedules, and quality control procedures that ensured their water-powered factories ran smoothly year after year. They were essentially running medieval corporations, complete with standardized procedures, trained personnel, and systematic approaches to problem solving. The division of labor was particularly sophisticated. Choir monks, who spent most of their time in religious observances, handled the intellectual work, designing improvements, calculating gear ratios, planning new installations. Lay brothers, who had taken simpler vows, operated the machinery and performed the skilled technical work. Hired workers handled the heavy labor and routine maintenance. This wasn't just a casual division of responsibilities. The monasteries developed formal training programs that turned farmers' sons into skilled millwrights, gear cutters, and mechanical engineers. They created what were essentially medieval technical colleges, passing down complex engineering knowledge through hands-on apprenticeships that could take years to complete. The expertise they developed was jealously guarded. Monastery workshops were off-limits to outsiders, and the monks were forbidden from sharing their technical secrets with competing operations. This wasn't just about protecting trade advantages. It was about maintaining the economic foundation that supported their religious communities and charitable work. But keeping all this medieval machinery running smoothly was like trying to conduct an orchestra where half the instruments were made of wood. The other half were powered by flowing water, and everything could break down at the worst possible moment. The monks didn't just build these systems and hope for the best. They developed maintenance routines that would make modern factory managers weep with envy. Every morning before dawn prayers, teams of lay brothers would begin their inspection rounds with the methodical precision of airline mechanics. They'd start at the trash racks, those seemingly simple metal gratings that kept leaves, branches, and dead fish from jamming the water wheels. You might think cleaning a metal grate would be easy, but try doing it when there's 1,000 gallons per minute of ice-cold water rushing through it, and you'll quickly realize why this job required both courage and considerable upper body strength. The trash racks weren't just randomly placed pieces of metal. They were carefully designed with bar spacing that was wide enough to let water flow freely, but narrow enough to catch anything that might damage the delicate wooden gears downstream. Different seasons brought different challenges. Spring meant dealing with tree branches and flood debris that could weigh hundreds of pounds. Summer brought algae growth that could clog the finest mesh. Fall meant endless leaves that would mat together like medieval filter paper. Winter meant ice formations that could crush the strongest iron bars. The monks developed specialized tools for each type of blockage. Long-handled rakes for pulling out branches, curved scrapers for removing algae, iron picks for breaking up ice dams. Some monasteries even trained their lay brothers in what we'd now call swift water rescue techniques, because clearing a jammed trash rack often meant working in conditions that could sweep a grown man downstream faster than you could shout for help. From the trash racks, the inspection teams moved to the bearing points, those critical spots where wooden shafts rotated inside wooden housings. Medieval bearings didn't have ball bearings or roller bearings or any of the fancy engineering we take for granted today. They were basically wooden holes that wooden shafts turned inside, kept smooth by constant application of animal fat and careful alignment. The lubrication process alone was a daily ritual that required the skill of a surgeon and the nose of a wine taster. The monks used different types of fat for different applications. Pig fat for the heavy-duty bearings that supported the main water wheels. Sheep fat for the delicate gear trains that required smooth, consistent operation. Fish oil for bearings that operated underwater or in constantly wet conditions. Each type of lubricant had its own application technique, storage requirements, and replacement schedule. But here's what made this maintenance system truly remarkable. The monks kept detailed records of every bearing, every gear, every mechanical component in their entire operation. They tracked which bearings failed most often, which lubricants lasted longest, which gear teeth wore out first. This wasn't just casual record keeping, it was systematic data collection that let them predict failures before they happened and optimize their maintenance schedules based on actual performance data. The pit clearance routine was perhaps the most dangerous part of the daily inspection. The pits that housed the main gear wheels had to be kept absolutely clean of debris, water, and the occasional small animal that wandered in looking for shelter. These pits were typically 6 to 8 feet deep, just wide enough for the massive wooden gears, and positioned directly under machinery that could crush a person faster than you could say workplace safety. Clearing these pits required nerves of steel and perfect coordination with the water wheel operators. The entire system had to be shut down, drained, and locked in position before anyone could climb down into the pit. But shutting down the system wasn't as simple as turning off a switch. Water had to be diverted through bypass channels, gear trains had to be locked in position with wooden chocks, and safety ropes had to be rigged for anyone working in the confined space. The monks developed hand signals and whistle codes for communicating during these operations. One sharp whistle meant stop everything immediately. 2 long whistles meant restart the water flow slowly. 3 short blasts meant someone was in trouble and needed help right now. These signals were practiced until they became second nature, because a miscommunication in a pit full of massive gears could mean the difference between going home with dirty clothes or not going home at all. Seasonal adjustments turned routine maintenance into an art form that required understanding water behavior at a level that would impress modern hydraulic engineers. Spring floods could increase water flow by 500% overnight, creating pressures that could burst sluice gates, overflow channels, or wash out carefully constructed embankments. The monks had to be ready to redirect this surge of power without losing control of their entire system. Their flood management techniques were ingenious. Overflow channels that normally carried a trickle of water could be opened to handle massive flows during spring runoff. Adjustable weirs could be raised or lowered to maintain optimal water levels in the mill pond. Emergency spillways could dump excess water safely away from the monastery buildings. Some systems even had what amounted to medieval circuit breakers, automatic gates that would open when water pressure exceeded safe limits, protecting the machinery even if no one was around to operate the controls manually. Summer droughts presented the opposite challenge. When stream flow dropped to a fraction of its normal volume, the monks had to squeeze maximum efficiency out of every gallon. They developed water conservation techniques that would make modern environmentalists proud. Smaller operations were shut down to concentrate available power on essential activities. Water wheels were adjusted to work with lower flow rates. Some monasteries even had backup systems that could operate on stored water when stream flow dropped below critical levels. The gear ratios themselves had to be adjusted seasonally. High water periods meant the wheels turned faster, which could overspeed delicate operations like flour grinding. Low water periods meant slower wheel speeds that might not provide enough power for heavy work, like fulling cloth. The monks solved this by creating modular gear systems that could be reconfigured for different conditions. Changing gear ratios wasn't like shifting gears in a modern car. It meant physically removing wooden gears that might weigh hundreds of pounds, replacing them with different sizes, and realigning the entire drivetrain. This work required teams of skilled craftsmen working with wooden cranes, rope pulleys, and mechanical knowledge that was passed down through generations of monastic engineers. Winter brought its own unique challenges, particularly in northern monasteries where temperatures could freeze the entire water system solid. The monks developed heating systems that used the waste heat from their forges to keep critical water channels from freezing. They built insulated housings around sensitive machinery. Some monasteries even created underground channels that stayed warm enough to keep water flowing when surface streams were locked in ice. But the real test of these maintenance systems came when something went seriously wrong. Burst sluices were particularly dramatic failures that could flood entire workshops in minutes. The sluice gates that controlled water flow were under constant pressure, built from wood that expanded and contracted with temperature changes, and operated by mechanisms that were subject to wear and occasional human error. When a sluice gate failed catastrophically, and they did, with disturbing regularity, the monks had to respond with the speed and coordination of a modern emergency response team. Emergency procedures were drilled until they became automatic. Teams of workers knew exactly which channels to open to divert the flood, which machinery to shut down first, which materials to grab for emergency repairs. The repair techniques they developed were masterpieces of medieval engineering improvisation. Temporary dams could be built from sandbags, wooden planks, and whatever else was available to redirect water flow, while permanent repairs were made. Emergency gates could be fashioned from available materials and installed in a matter of hours. Some monasteries kept prefabricated repair components in storage, ready to be deployed when disaster struck. Worn cogs presented a different type of challenge. The wooden teeth on gear wheels were subject to constant stress and would eventually wear down or break off entirely. When this happened gradually, the monks could often compensate by adjusting other parts of the system. But when multiple teeth failed simultaneously, the entire gear train could jam or worse, tear itself apart in a cascade of wooden destruction. The monasteries developed sophisticated gear replacement techniques that let them swap out damaged components without shutting down the entire operation for days. Temporary bypass systems could reroute power around damaged gears. Modular gear designs meant that individual sections could be replaced rather than entire wheels. Some of the larger monasteries even maintained gear-cutting workshops that could manufacture replacement parts on site. Jammed hammers in the forge were perhaps the most dangerous type of failure. A tilt hammer weighing several hundred pounds that suddenly stopped mid-stroke could destroy its mounting, damage the cam system, or even break the main drive shaft. The forces involved were enormous, and the potential for catastrophic failure was always present. The monks developed quick-release mechanisms that could disconnect jammed hammers from the drive system before serious damage occurred. These safety devices were purely mechanical: springs, levers, and carefully calculated weak points that would fail in a controlled manner, rather than letting destructive forces propagate through the entire system. But what really set the Cistercian maintenance system apart was their approach to systematic improvement. They didn't just fix problems, they analysed why problems occurred and designed better solutions. Bearing failures led to improved lubrication systems. Gear wear patterns led to better tooth designs. Seasonal flooding led to improved water management. This continuous improvement process was formalised through their network of monasteries. Technical innovations developed at one location were shared with others through a system of travelling technical specialists. A better design for water wheel paddles developed in France would find its way to monasteries in England within a few years. Improved gear cutting techniques discovered in Germany would spread throughout the Cistercian network. The numbers behind all this maintenance work were staggering. A typical monastery might employ 20 to 30 skilled craftsmen full-time, just keeping their water-powered systems running. They consumed enormous quantities of lubricants, replacement parts, and raw materials. One monastery's records show they used over 2,000 pounds of animal fat per year, just for bearing lubrication. Another consumed 500 cubic feet of hardwood annually, just for gear tooth replacements. But all this maintenance and repair work was worth it because of the incredible productivity these systems could achieve. When everything was running properly, the output was genuinely mind-boggling. A single water-powered grain mill could process more wheat in a day than 10 traditional hand-operated mills. The cloth production rates were even more impressive. Water-powered fulling stocks could finish cloth at rates that would have required dozens of workers using traditional methods. The economic calculations that justified all this complexity were surprisingly sophisticated. The monks understood concepts like return on investment, operational efficiency, and productivity optimization centuries before these became formal business principles. They tracked production rates, calculated maintenance costs, and made investment decisions based on quantitative analysis of their operations. Their record-keeping systems were so detailed that modern historians can reconstruct not just what they built, but how well it worked. We know that a typical Cistercian water wheel generated roughly 3 to 5 horsepower, not much by modern standards, but revolutionary for the medieval period. We know that their gear systems operated at efficiencies of 60 to 70%, meaning most of the water wheel's power actually reached the working machinery rather than being lost to friction. The production numbers are equally impressive. A water-powered grain mill could produce about 150 pounds of flour per hour when operating at full capacity. That might not sound like much, but it was enough to supply bread for several hundred people. A fulling operation could process about 50 yards of cloth per day, compared to perhaps 5 yards for hand fulling. A water-powered forge could produce iron goods at rates that would supply an entire region's needs for tools, horseshoes, and hardware. But perhaps the most remarkable aspect of these medieval factories was how they integrated so many different operations into a single, coordinated system. Modern factories tend to specialize in producing one type of product. The Cistercian monasteries were more like medieval versions of Amazon warehouses. They produced everything their communities needed, from food to clothing, to tools, to building materials, all powered by the same water source and managed by the same organizational system. This integration created efficiencies that wouldn't be seen again until the Industrial Revolution. Waste products from one operation became raw materials for another. Heat from the forge warmed other workshop areas. Water used for washing wool was recycled for other cleaning operations. Nothing was wasted. Everything was optimized, and the entire system worked together with a precision that would make modern lean manufacturing experts jealous. The site planning that made all this possible was itself a masterpiece of medieval engineering. The monasteries didn't just build their workshops wherever land was available. They carefully analyzed topography, water flow, seasonal variations, and operational requirements to create integrated manufacturing complexes that maximized efficiency while minimizing construction costs. The typical layout followed the water source from upstream to downstream, with each operation positioned to take advantage of the optimal water pressure and flow rate for its specific requirements. Heavy grinding operations that needed maximum power were placed closest to the main water source. Lighter operations that could work with reduced flow were positioned further downstream. The final operations, like washing or cleaning, used the last of the water's energy before it returned to the original stream. This sequential arrangement meant that every drop of water was used multiple times before being released, maximizing the energy extraction from the available flow. It was like having a series of hydroelectric plants in miniature, each one capturing a portion of the stream's energy before passing the water along to the next stage. The efficiency of these systems was remarkable. Some monasteries extracted so much energy from their water sources that the streams leaving their complexes flowed noticeably slower than the streams entering them. The genius of this water management extended far beyond simple engineering. It was economic warfare disguised as monastic efficiency. While other communities struggled with seasonal production cycles, the Cistercians had created something that operated like a medieval stock exchange, where water flow translated directly into market dominance. Their standardized production methods meant they could flood regional markets with goods that were not just cheaper, but consistently better quality than anything produced by traditional craftsmen. The gear standardization system they developed was particularly brilliant. Instead of each monastery inventing its own mechanical solutions, the Cistercians created what amounted to medieval industrial standards. A gear cut at a monastery in France would fit perfectly into a mechanism built at their sister house in England. This interchangeability meant they could mass-produce replacement parts, share technical improvements across their entire network, and maintain their equipment with an efficiency that left competitors scratching their heads. But here's what really separated these monastic engineers from everyone else: their obsessive record-keeping turned guesswork into science. While other mills operated on tradition and hope, the Cistercians measured everything. Flow rates, gear ratios, production outputs, maintenance schedules, they tracked it all with the dedication of accountants and the precision of scientists. One surviving ledger from a French monastery shows daily water measurements taken at 6 different points along their system, recorded for over 30 years straight. This data collection wasn't just academic curiosity. They used these numbers to optimize their operations in ways that wouldn't become common in secular industries for centuries. They knew exactly how much grain they could process per gallon of water flow. They calculated the precise relationship between hammer speed and iron quality. They even tracked seasonal variations in wood moisture content and adjusted their gear cutting schedules accordingly. The disciplined approach to continuous improvement created a feedback loop that kept pushing their technology forward. When a gear design lasted longer than expected, they analyzed why and incorporated those improvements into future builds. When a water wheel performed better in certain conditions, they studied the variables and replicated the success. This wasn't random tinkering. It was systematic engineering development that laid groundwork for the scientific method itself. The economic impact of this systematic approach was staggering. By the 13th century, some Cistercian monasteries were operating what can only be described as medieval manufacturing conglomerates. They weren't just meeting local needs. They were exporting finished goods across Europe, undercutting traditional craftsmen with superior products at lower prices. Their water-powered factories had essentially created the world's first industrial economy, hidden behind monastery walls and powered by nothing but flowing streams and relentless innovation. So there you have it, the real story of how a bunch of monks in white robes accidentally invented the Industrial Revolution 5 centuries early. While the rest of medieval Europe was still grinding grain by hand and beating cloth with sticks, the Cistercians had figured out how to make rivers work like employees, gears function like computers, and water flow like electricity through their stone-walled factories. These weren't just religious communities praying and copying manuscripts. They were engineering geniuses who turned streams into assembly lines, created medieval quality control systems that would make modern manufacturers jealous, and developed maintenance routines so sophisticated they kept wooden machinery running for centuries. They proved that innovation doesn't need silicon chips or steel. Sometimes all you need is flowing water, wooden gears, and an obsession with efficiency that borders on the fanatical. The next time you flip a switch or start your car, remember those medieval monks who figured out how to harness nature's